So welcome all of you to today's lecture of machine design, and I'm going to start with the chapter theories of failure. This is the heart of machine design, this chapter theories of failure. If you understand this chapter theories of failure, you will understand every chapter in machine design. So watch this video patiently, and at the end of this video, if you have any doubt, please comment on the comment section, and please subscribe to my channel so that you don't miss any important videos. Okay, so without wasting any time, we are going to start. See, there are different failure theories, but in today's video we are taking only these two theories. We will talk only about these two theories. The rest theories I will explain in next lecture. Okay, so we will talk about maximum principal stress theory and maximum shear stress theory. Okay, so let's start with maximum principal stress theory. Maximum principal stress theory. Okay, so I will start with the example. Suppose there is a component, there is a mechanical component which is subjected to stresses, which may be subjected to biaxial, that means stress in two directions, or triaxial in three directions, biaxial or triaxial stresses. Suppose this is a mechanical component, it is subjected to triaxial stress. We will consider triaxial stress. Just an example. Okay, we will consider triaxial stress. Suppose my stresses induced in this body are sigma 1, sigma 2 and sigma 3 in three directions because triaxial. Now, for just take an example that this is your condition. Sigma 1 is the maximum principal stress. Sigma 1, sigma 2, sigma 3. These are principal stresses induced in this body. Now, among these three principal stresses, sigma 1 is the maximum. Okay, this is the maximum. Now, we have to find that what should be the value of sigma 1 so that my this component is safe. It is not, failure does not occur to this component. Whether this component is brittle or ductile, that is, we will come to that. But for the time being, you have to find that whether this sigma 1 is safe or not. Okay, we will find that. And for that, we will understand maximum principal stress theory. Now, suppose if you take the same material, suppose I am writing here same, that is same material, this component and this component are same, but now this component is subjected to uniaxial stress, or suppose you are performing a simple tensile test. You are performing a simple tensile test. We only give uniaxial tensile force. Now, due to this application of tensile force, you will find that this object has two values, SYT and SUT. Of course, there will be two stresses, SYT and SUT. Okay, that means what? Try to understand. Very simple. You have applied some tensile force, and due to that tensile force, SYT amount of stress is induced. SYT is what? It is the yield stress in tension. It is the yield stress in tension. And suppose if you have gone on increasing the load, then what will happen? a stress will induce that is known as SUT, or ultimate tensile strength, maximum amount of tensile force it can withstand. You apply a more tensile load, it will fail. Suppose, for example, you have found out that this value of SYT from the test is 150 megapascal and this value is 300 megapascal. Very simple. You have applied load tensile force in one direction and you have found these values. And the same material was subjected to triaxial stress in the previous condition. Now, maximum principal stress theory, also called Rankin's theory, because it was proposed by Rankin. This theory states that this mechanical component which is subjected to triaxial stress is going to fail when the maximum principal stress, which one is the maximum principal stress? Sigma 1. When this maximum principal stress will be equals to the yield strength or the ultimate tensile strength of the material. That means this material is going to fail. Failure will occur. Failure will occur when failure is going to occur when sigma 1 is equals to SYT or sigma 1 equals to SUT. But I am going to write a very important sentence just below it. Very important. Whichever applicable, these two are conditions that material is going to fail, but this term is very important, whichever applicable. Okay, now I am going to tell you that whether maximum principal stress theory is suitable for ductile material or for brittle material. When I am going to explain you this thing, your concept is going to clear. Here I have written one thing in my introduction page, that for brittle material this is the condition. For brittle material this is my condition. It is weakest in tension. Then shear, then compression. Okay, that means brittle materials have the most chance of failure in tension, not in shear, not in compression. In compression there is no chance at all, because in compression brittle material is strongest. And similarly for ductile materials, it is going to fail under shear. Then there is chance of tension, and actually this condition may not be applicable. You can also say that compression for ductile materials I am talking equals to tension greater than shear, because in many books you will find that this is true, that ductile materials are weak and weakest in shear. This you can tell from your common sense also. You think of about any ductile material, you can feel from your intuitions that the ductile material has the most chance of failure under shear. The tensile strength and the compressive strength for ductile materials are same. But for brittle material, always remember compressive strength is much higher than the tensile strength, also than the shear. But for ductile materials, compressive strength is equals to tensile strength. So we can understand from this that whenever we want to design brittle material, we have to design considering the tensile load or tensile strength, and whenever we are going to design for ductile materials, we have to design considering shear strength, because first it is going to fail under shear most probability. Okay, now tell me one thing, that when we have studied about maximum principal stress theory, have we talked about shear stress? We have considered these conditions: SYT, SUT. This is ultimate tensile. This is yield strength in tensile. Yield strength in tensile. Okay, we have not considered about shear. So in maximum principal stress theory, we are designing a material by considering the tensile load or tensile strength. So maximum principal stress theory is applicable for brittle materials. Okay, so we can conclude that this maximum principal stress theory is applicable for brittle materials. Now, if you have understood this, you can understand maximum shear stress theory easily, and once after understanding maximum shear stress theory, your concept in maximum principal stress theory is going to be much more clear. Okay, so we will start with maximum shear stress theory. The logic and the fundamental thing is same. Maximum shear stress theory. Okay. Now, same thing, suppose this is your mechanical component. It is subjected to three states of stresses: sigma 1, sigma 2, sigma 3. Same triaxial stresses induced in this due to loading in three different directions. Let the condition be same. So we have to consider this thing in mind, that is sigma 1, that is the maximum principal stress. Okay, now very important thing, that suppose, let us assume that maximum shear stress theory is for ductile materials, then it will be easy for you to understand. And I have explained little bit already that why it is for ductile materials. Suppose that it is for ductile materials. Now, since it is for ductile materials, we have to consider the shear strength. We have to find the maximum shear strength of this material, because once the maximum shear strength of this material is crossed, then the yielding will occur, and that yielding is actually yielding or failure. In ductile material, failure of ductile material means yielding, because once a ductile material is plastically deformed, permanent deformation occurs to that, then it is of no use. It is, we call it failure. Okay, so try to understand. We have to find the maximum shear stress. We have to find the maximum shear stress that is induced. We have to find the maximum shear stress that is induced, or the maximum shear strength of this material. So we have to find this. Now, again, get back to the same logic, that this is your mechanical component and it is loaded uniaxially. That means simple tensile test has been performed. Okay, and you will observe that at some point of load, at some value of load or strain, a stress is going to be induced that is equals to the yield strength. Yield strength in tension. That means yielding will start. Now you have to find the maximum shear stress. We will find with the help of Mohr's circle. Mohr's circle. Try to understand. Mohr's circle is very simple. This is your origin. This is your origin. If you have any doubt in Mohr's circle, don't worry. Comment in the comment section. I will make one video on how to draw Mohr's circle. This is your origin. This is your SYT from origin to here. SYT. Take this as the center and with this as radius, draw the Mohr's circle. And we always know that the radius of the Mohr's circle, that is R, radius of the Mohr's circle is the value of the maximum shear stress, which is nothing but SYT by 2, because this radius is half of SYT. Total was SYT, half is SYT by 2. Half of SYT by 2. So we come to the conclusion that tau max is SYT by 2. Tau max is what? SYT by 2. That means what? Shear is taking place when at half of the yield strength in tensile. Suppose I am giving you example, don't worry. SYT was 150 megapascal. That means yield strength in tension was 150 megapascal. Try to understand. Many people have the confusion that I am giving only tensile force, no shear. Then how shear force is going to develop in the body? Yes, you are giving only tensile force. You are not giving any tau in this way. No shear force externally, but still shear force is going to generate inside the body. Okay, because I'm just giving a brief explanation. When you are pulling this material, the fibers of this material may slide over each other. Suppose this is one fiber and this is another fiber. This fiber may slide against each other. In this way, shear force is developed and ductile materials have huge probability of getting sheared up. So this thing also means that yield strength in shear is equals to half of yield strength in tension. Yield strength in tension was SYT and yield strength in shear is just half of it, because at that point, at half of that SYT only, my tau is maximum and the material is going to fail at that point only. Okay, when tau is maximum. So for my ductile materials, design criteria is this thing. Tau max is my design criteria. Tau max. And so this thing we have understood. And one thing I have not told you is factor of safety. So you have understood that why we use maximum shear stress theory for ductile materials, because ductile materials are weakest in shear. So we have to consider what is my maximum shear strength. Okay. Now I have not told you about factor of safety. Just let me tell you factor of safety. Suppose first just let me tell you or explain this with the help of maximum principal stress theory. Maximum principal stress theory. For example, you are going to design a ductile material, brittle material. For example, you are going to design a brittle material. Then failure will not occur. Failure will not occur if the value of the maximum principal stress is less than SUT or ultimate tensile strength. If it is less than ultimate tensile strength, failure is not going to occur. For example, this is 290, this is 300. Failure, you know that failure is not going to occur, but there is a very risk. There is a great chance of risk. That means if this value of sigma 1 or principal stress increases suddenly, then your material will fail. And brittle materials fail, you know how it fails, by crack formation. You will not get any time, because if it suddenly increases, it will be very close to 300. So where safety is a major concern, where human lives are involved, in railways like this thing, in bridges, factor of safety is very important. What do we do by factor of safety is that we reduces the value of sigma 1. Sigma 1, or you can say this as working stress, or you can say this as limiting stress, different name, or you can say this as allowable stress, same thing. So sigma 1 will be SUT by 2. SUT by 2. SUT by factor of safety. First write factor of safety. SUT by factor of safety. Suppose factor of safety is 2 or 3. I have considered 2 first. That's why I have written 2. Okay, consider 3 now. Then what was your SUT? 300 divided by 3. It is 100. 100 megapascal. That means what? This value of sigma 1 must not cross 100. It must be at 100. You can keep it at 90, you can keep it at 80, but 100 is okay. Do not go more than that, because that may be proved risky. Okay. I know that it will not going to fail until and unless it reaches 300. But still, for safety purpose, we will consider it 100. So we have considered that sigma 1, or the stress, maximum stress that can be induced, or the limiting stress, or the working stress, must be is equals to 100 megapascal. So my load should be such that the stress that will be induced due to that load must not be more than 100 megapascal in this example. In similar way, you will also consider for ductile materials also. In shear stress theory, how factor of shear stress theory for ductile materials, how you can use factor of safety? Same, tau max is equals to, tau max I have told you it will be SYT by 2. Okay, and then divide this value with factor of safety. Okay, SYT by 2 we have proved. And then you have to divide this value with factor of safety just to reduce the value of tau max. Okay, same logic which I have explained in this case, same logic here also. So this was my video, and if you have any doubt, please feel free to comment in the comment section. Okay, thank you very much.